Well, hello. We meet again. This is Mr. Minnick. And this time, what we're going to talk about in the unit circle are the coordinates, where they come from. And I know at this point in time, many of you are probably thinking to yourself, well, I just want to know what they are. Or maybe I already know what they are and I just want to take this silly test. Well, remember in part one what I said, I'm going to stick to. I said a lot of times if you know why something is what it actually is easier to find out. Okay? So on the test that you're going to take, one question deals with a reference triangle. Okay? So I'm going to go ahead and just trace out a reference triangle here. So there's a radius. Remember, the unit circle has a radius of 1. So there's the radius of this triangle. And then I'm going to drop what's called an altitude, which is a vertical line from the end of that ray down to the initial ray. And then I'm going to go across then with the base of this triangle. Okay. So what I've got there then, if I can group all that together and cut it out of there, I'll just go ahead and clone it. What I've got, that's called a reference triangle. Okay. That's a reference triangle. Reference triangle. So the deal is, on the test, on the last page, one question says, to what part of the reference triangle does the radius correspond? So if we look at the radius, it's 1. What part of the reference triangle is that? And the question will even tell you, is it the hypotenuse, is it the short leg, or the long leg? And I think it's pretty clear, I hope it's pretty clear now, that the radius of the unit circle corresponds to the hypotenuse of this reference triangle. Okay. So, what we're going to do then, when we get to these coordinates in just a minute, is we're going to figure out what they are, and we'll look at the theory behind where everything comes from. And then we'll go over how to memorize those coordinates, okay? So if we look at this particular triangle, it's bisecting the 0 and the 90, so it's a 45-degree triangle. So technically this would be an isosceles right triangle, 45, 45, 90, okay? But I'm just going to kind of take that 45 out of the equation for a minute, or out of the triangle for a minute. So what I would like to do then is go ahead and cut that out, and we'll just paste it on a clean page here. Okay. So on this triangle, I know what the radius is, and if I had to calculate the lengths of the legs, I don't know what they are. But I do know that they're the same because it's an isosceles right triangle. Let's give it a variable. Let's call it x. And x, okay? So I know by the Pythagorean theorem, x squared plus x squared equals 1 squared. So 2x squared equals 1. So x squared equals a half. So if I take the square root and take the square root, I get x equals the square root of 1 over the square root of 2, which is 1 over the square root of 2. And you might remember this from a couple weeks ago when we simplified radicals. That you need to multiply this by rad 2 over rad 2, which gives you rad 2 over rad 4, which gives you rad 2 over 2. Okay? Rad 2 over 2. Rad 2 over 2. So, the deal then is, in this reference triangle that we were looking at, the length of a leg, or the base of it, is rad 2 over 2. Now remember, we said that the other side is the same length. So the other side is also rad 2 over 2. Okay, so hopefully at this point everybody's doing okay. Now one thing you might have noticed, maybe did, maybe didn't, I don't know. But in the trig homework, what they asked you to do was to find the cosine of pi over 4, or 45 degrees. Okay. Well, if you think about this, we had what, rad 2 over 2 and rad 2 over 2 here. Okay. So the cosine by definition is the adjacent over the hypotenuse. And the adjacent side is it's that rad 2 over 2. So rad 2 over 2 over 1 is just rad 2 over 2. Okay? So the deal is the cosine of 45 degrees is rad 2 over 2. It's the length of that adjacent side. It's the length of that adjacent side. Okay? In a similar fashion, then the sine of 45 degrees would be something over 1. And the something that it is, it's the OPP. It's the opposite. It's the side opposite that 45-degree angle. It's the side opposite. So it's this rad 2 over 2 over 1, which ends up being just rad 2 over 2. So the sine of 45 degrees is also rad 2 over 2. Okay? You might say, well, what does this have to do with the unit circle? Well, we're getting to that. Okay? So, let's bring back in a unit circle. Let's bring in our triangle here then. Okay? So remember, on the unit circle, we've got coordinates here. We've got coordinates here. And those coordinates, it's x, the x value, and y, xy, right? Well, a second ago we said that the cosine, get out my highlighters here if I can. A minute ago, or a second ago, a couple minutes ago, we said that the cosine, now the nice thing is, since it's a unit circle, the radius is 1 and that part's irrelevant. We said the cosine is in effect the length of this adjacent side. Well, if we look at the length of that adjacent side and think a little bit, the center of this unit circle, the bottom vertex of this triangle, is at the center of the unit circle, which is 0, 0. And if we were to go across that far, if we were to go across that far, we went rad 2 over 2. That's a horizontal distance, and horizontal distances in the Cartesian plane are also known as x-coordinates. Okay, so the deal is the x-coordinate at that point is the rad 2 over 2. Okay. Furthermore, what that means, we said that's the cosine. What that means is anytime you're dealing with coordinates of the unit circle, the x-coordinate is the cosine at that given angle. The x-coordinate is the cosine at that given angle. So the cosine of a particular angle measure corresponds to the x-coordinate at that point on the unit circle. It's really profound, it's really cool, it's really awesome the way this all works. So in a similar fashion then, if we think about the vertical height, it was rad 2 over 2. That vertical height is rad 2 over 2. That's our y value. It's rad 2 over 2. And what ends up happening then, we said that vertical height was the sine. And I know I'm making a mess here on this graph, but just bear with me for one more minute. So the sine, we said, was the length of this vertical height. So the deal is the y coordinate of any given point then on the unit circle corresponds to the sine, to the value of the sine function on the unit circle. Okay? So there's going to be questions on the last page of the test. Just remember this. X is the cosine. Y is the sine. X is the cosine. Y is the sine. How can you memorize that? Well, alphabetic order predominates in math a lot of times. Cosine, sine. Okay? Really profound statement there. So, are you telling me then that I can apply this to the coordinates of the unit circle that I already know? Well, sure, that's exactly what I'm telling you. So, we're going to take a minute with the calculator here. 0 degrees, or 360 degrees, otherwise known as 0 pi radians, or 2 pi radians. The coordinates over at that point, remember, are 1, 0. So on my calculator, if I calculate the cosine of 0, and I got to check how my calculator's set up. So I'm going to go into my settings. I'm going to go home and settings, document settings. So my calculator's set up for angles in radians, okay? Angles in radians. So if I calculate the cosine, and it's on this trig button, here we go, the cosine of 0. The cosine of 0. Remember, that should correspond to the x coordinate. So I'm expecting the cosine of 0. Hopefully everybody's on the same page and following along. The cosine of 0 had better be 1. Check it out. Cosine of 0 is 1. Similarly, if I calculate the sine, not the inverse sine, but the sine, where's the sine? Oh, it's right there. The sine of 0 should be the y coordinate there. So the sine of 0 should be 0, and it is. Okay. Oh, so you mean we can do this on the other parts of the unit circle as well? Absolutely. That's exactly what I'm saying. So if we think at 90 degrees here, at 90 degrees, or if you want pi radians, that's going to be pi over 2 radians. Remember what the coordinates there are. It's 0, 1. So let's go with the cosine of 90. Remember the cosine we said is the x coordinate. So the cosine of 90 ought to be that 0. Oh, yeah, that's right. The calculator set up for radians. So let's go cosine. It was pi over 2. Cosine at pi over 2. So cosine of pi over 2. There's the 0. And then sine at pi over 2. Sine at pi over 2. Well, that should be the y coordinate, and it should be 1. And it is. So you mean to tell me I don't even need a calculator to calculate sine, cosine, and maybe tangent? Well, yeah, that's what the unit circle is all about. It's about finding a way to calculate sine, cosine, tangent, secant, cotangent of all these angle measures without a calculator. It's really an ingenious device. So again, moving around the circle then, if we were to go out to 180 degrees, otherwise known as pi radians, looking at the coordinates of -1, 0, again, the cosine of pi should be -1. Check it out. The cosine of pi is -1. Similarly then, the sine of pi should be the 0, and it is. Okay. Let's go back and look at that 45-degree angle we were talking about, because the sine and cosine should have been rad 2 over 2. And this one's a little tricky. And people like decimals. I'm not a big fan of the decimal, but so let's look at the cosine. That was the x-coordinate. So the cosine at 45 degrees is pi over 4. So the cosine at pi over 4 is 0.707. So if we take the decimal equivalent of that, radical 2 over 2, it is 0.707, okay? So then if we look at the sine of pi over 4, sine of pi over 4, that should be that 0.707 again, and it is, okay? So, you mean we could do this the rest of the way? Absolutely we could. So let's go ahead and start filling in some of these coordinates then, okay? So I'm going to go ahead and lock this in place. And I'm going to fill in the coordinates at the quarters. I call these the quarters, sometimes the corners. Remember, I like to make a box with a vertex with all these vertices around it. So if I make a box like so, at each vertex of that box, remember, it's going to be a fourth of a pi. It's going to be some fourth of a pi. It's going to be some fourth of a pi. It's going to be some fourth of a pi. And remember, count 45 degrees at a time. 1 pi over 4. 2 pi over 4 we don't need to write because that's got a different fraction. So then we're at 3 pi over 4, right? And then 4 pi over 4 we don't write because that's just pi. And then, so this one's 5 pi over 4. We go another 45, and that's at 6 pi over 4, but the fraction's different. So then we're back to 7 pi over 4, okay? So let's look at the coordinates of this, and let's use a little bit of what we know about the Cartesian plane to help figure this out. So respective to the Cartesian plane, we've got the origin here. We've got quadrants 1, 2, 3, and 4. And we know the signs are plus, plus, minus, 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 and plus, minus. Okay? So that should help us because check it out. With our 45-degree reference triangle, we had rad 2 over 2, rad 2 over 2. The great thing about all that is this. Symmetry comes into play. Knowing the Cartesian plane comes into play. Knowing the signs in the Cartesian plane comes into play. Okay? What I'm saying is every coordinate there is going to have the same quote-unquote numbers in absolute value. Okay? It's going to be a rad 2 over 2 and rad 2 over 2. But what's going to happen is in quadrant 2, the sign SIGN, the SIGN, the sign of the cosine is going to be negative because the x-coordinate is negative. Okay, let me highlight that and bring some attention to that. So we have a negative sign there because in quadrant 2, the x values are negative. Okay, hopefully you catch that. So if we go down then to quadrant 3, down to 5 pi over 4, the signs are negative, so we're going to have negative rad 2 over 2 and negative rad 2 over 2. Okay? And then finally with the 7 pi over 4, the x-coordinate, the cosine, it's going to be positive, but the y-coordinate, the SIN, the sign, the SIGN of the SINE is negative. So we're going to have a negative there. Okay? So those are the coordinates at the quarters or the corners. Okay? Always going to be rad 2 over 2 for both the x and the y because of the nature of the isosceles right triangle. Always going to see a rad 2 next to a rad 2. Okay. So, what's next now is a different kind of triangle. Different kind of reference triangle. Now the cool thing is that you learned about a 30, 60, 90 right triangle. So if we do the 30, we'll get the 60, and if we do the 60, we'll get the 30. So we're going to kind of, to use a metaphor, kill two birds with one stone here. Okay. So here's our 60-degree reference triangle. Okay. So let me see if I can group all that together. See if I can clone all that. And there we go. So remember the radius is 1. And I don't know what theorems, what postulates, what definitions you remember from geometry. But I hope that you remembered a little bit about the 30, 60, 90 right triangles and remembered that the short leg is half the length of the long leg. I hope you remembered that. So the short leg is this base, okay? So that's going to be 1/2. So you might say, well, what about the other thing? Well, so 1/2 the quantity squared plus the other thing, and technically we should call it y because it's a height, because it's the SINE, the sign, plus y squared equals 1 squared. So we get a 4th plus y squared equals 1. So we get y squared equals 1 minus a 4th. So we get y squared equals 3/4. So we take the square root and we take the square root and we get y equals the square root of 3 over the square root of 4, which is the square root of 3 over 2. Square root of 3 over 2. So remember the x value is the horizontal distance, and that is the cosine. So if we look at our coordinates at this 60-degree reference triangle are these. they are 1/2 for the x. And remember, the y is the sine, the vertical height, and that's going to be radical 3/2. So you might say to yourself, well, how do you tell the difference between the two? Well, this is what I do. I look at this horizontal length, and then I compare that to this vertical height. That's what I do. And you might say, well, what does that have to do with anything? Well, I'll get to that in a second. So we're trying to figure out, of these two, this half and rad 3/2. If you just look at the fractions, you might not know how big rad 3 is, but you know that the square root of 1 is 1, and the square root of 2 then is going to be bigger than that. So the point is the square root of 3 is bigger. Okay? The square root of 3 is bigger than the square root of 1. So what we're saying is the square root of 3/2 is longer than or bigger than this 1/2. So one thing I want to say is this. 1/2 and rad 3/2 are like the following. They're like Tom and Jerry. Really showing my age here. They're like peanut butter and jelly. They're like Mutt and Jeff. Okay? In other words, they're constantly together, side by side, in holy matrimony, as long as they both shall live, till death do them part. You will always see them paired up. Always. You could probably think of some people in the building who are like that as well. Okay? Use your imagination. So anyway, you will always see 1/2 and rad 3/2 paired up like that. Okay. So just to kind of show you again, back to this whole degrees, radians, sine, cosine stuff. Remember, 60 degrees is pi/3. So if we found the cosine, of pi/3, the cosine of pi/3, we're expecting that to be the same thing as the x-coordinate at that point on the unit circle, which is 1/2, which is 0.5. Okay, similarly then, if we found the sine at pi/3, what we would expect is radical 3/2, and let's check. Radical 3/2, and there we go. Okay? So, 1/2 rad 3/2, they're like Tom and Jerry. You will always, always, always see them side by side. So, let's go ahead then and look at the coordinates at the thirds. Okay? So let me see if I can get this little box going again. At the thirds. So again, with these angle measures, it's going to be over 3. This one's going to be over 3 in pi radians, of course. This is over 3, and this one's over 3. Count pi/3 radians at a time, 60 degrees. 1 pi/3. Another 60 degrees, 2 pi/3. Another 60 degrees puts you at 3 pi/3, but that's just pi. So it was 3 pi/3. Another 60 degrees puts us at 4 pi/3. Another 60 degrees puts us at 5 pi/3. But we want the coordinates here. We want the coordinates. We want the coordinates. Now remember, the whole symmetry idea comes into play again. So at this third, it's going to be 1/2 and rad 3/2. And you might say, well, I don't know which is which. I don't know which one's the 1/2 and which one's the rad 3/2. Well, let's think. Let's not draw blue lines across the screen. Let's think. 1/2 and rad 3/2. One of them's smaller, so if you need to sketch in this to kind of figure out this first one, go ahead and do this. So here's my vertical height. Here's my horizontal distance. Which one of those two is bigger? Which one of those two is greater? Well, it looks like the red one's greater, and that's the The vertical height, that's the y-coordinate, so the rad 3 over 2 then is going to be the y-coordinate. The 1/2 is the x-coordinate. And so I'm going to have a half here, and I'm going to have a half here, and I'm going to have a half here. You might say, well, what about the signs? Well, we'll get to those in a second, okay? And then the rad 3 over 2. Remember, 1/2 and rad 3 over 2, they're always going to be side by side. So we'll have the rad 3 over 2, and we'll have the rad 3 over 2. Okay? So now just think of your signs. First quadrant, everything's positive. Second quadrant, the x's are negative. Third quadrant, both x and y are negative. Fourth quadrant, x is positive, y is negative. And there you go. Okay? One half and rad 3 over 2. They're always going to be paired up. They're always going to be teamed up. They're always going to be side by side. Like that. Okay? So the last thing we'll look at, and then we'll take some time to practice, is going to be the coordinates. Coordinates at the sixths. The nice thing is the sixths and the thirds are virtually the same. Virtually means almost exactly the same. So again, with this whole box thing, remember all these vertices here. If you need to draw that, do it. It's quite helpful. So sixths, 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 pi over 6. So that's pi over 6. 2 pi over 6, 3 pi over 6, 4 pi over 6. So that's 5 pi over 6. It's kind of hard to count by pi over 6s. 6 pi over 6 because it's 30 degrees at a time. Another 30 degrees, that's 7 pi over 6. That's 15 and 15, so that's another 30. So that's 8 pi over 6, but that has a special name. That's 4 pi over 3. 9 pi over 6, but that's 3 pi over 2. 10 pi over 6, so 11 pi over 6. Okay. So the coordinates here, you're saying, what's going on with these? Well, I've got news for you. We have another 30, 60, 90 right triangle. Hey, 30, 60, 90 right triangle. The radius is 1. The short side is half that. And the other side then is 1/2 and rad 3 over 2 are a pair, so that's rad 3 over 2. So it's rad 3 over 2 and 1/2. Okay. So again, symmetry comes into play. Symmetry comes into play. So we're going to have the same coordinates, just different SIG and S, different signs. Okay. So remember your quadrants. Quadrant 2, the x is negative. Quadrant 3, x and y are both negative. Quadrant 4, just the y is negative. And there you go. There you have it. That's all the coordinates of the unit circle. There they are. So at this point, you're probably thinking, well, how can I memorize this? I'm not going to be able to do this. Well, on that end, I've got a little trick that I saw watching, of all things, a YouTube video. What? You watch YouTube? Yeah, I watch YouTube. Of course I watch YouTube. So on these interior angle measures, everything's going to be over 2 all the time. Everything's going to be over 2 all the time. Everything's going to be over 2 all the time. Okay? Everything is going to be over 2 all the time. Everything's going to be over 2 all the time. Everything's going to be over 2 all the time. I sound like a broken record, I know. And we know that the x coordinates in quadrant 2 are going to be negative, negative, negative. Okay? So you might say, well, I don't get it. What's your trick? Well, my trick is this. This is as easy as 1, 2, 3 down. Well, you say, well, what about the other stuff? Well, remember what gets paired up. Remember what gets paired up. Rad 3 over 2 is always paired up with a half. So it's 1, 2, 3 back up the other side. It's 1, 2, 3 and 3, 2, 1. Or 1, 2, well, 1, 2, 3 down, 1, 2, 3 up. There you go. Well, how do I know if I'm starting with the right thing? Well, just be careful. So suppose you're on the other side and you don't know this little 1, 2, 3 down and 1, 2, 3 up, and you don't know to start with 1 and a 3. So check this out. Here's my reference triangle. How does this vertical height compare to this horizontal distance? Well, the horizontal distance is smaller. That's right. So the horizontal distance, the x-coordinate is the 1. So it's 1, 2, 3 down again. And rad 3 over 2 is paired up with a half, so it's 1, 2, 3 back up the other side. Oh, okay, well that kind of makes a little bit of sense, I hope, maybe. Be careful on the bottom. Be careful on the bottom. Again, all these interior coordinates are going to be over 2 and over 2. In the fourth quadrant, the y's are negative, right? So again, it's going to be over 2 and over 2, the y's are negative. Got to be careful on these ones in the bottom half, though, in the southern hemisphere, as it were. Okay. Again, over 2, over 2, over 2, over 2, and the x and the y are both negative in quadrant 3. Okay. So you might say, well, is this one 1, 2, 3 down? Well, be careful. Be careful. If you don't know what the first one is. Let's look. Let's look at our reference triangle. Altitude back to the x-axis. Go across like that. There's my reference triangle. There's my reference triangle. So what I'm doing is I'm comparing this horizontal distance, that horizontal distance, to that vertical height. The horizontal distance is bigger. The horizontal distance is the x value. So this is going to be 3, 2, 1 down. Well, what's paired up with a half? Well, 1/2 and rad 3 over 2. They're like peanut butter and jelly. So rad 3, 2, 1 back up. Okay. And again, symmetry on the other side. Symmetry on the other side. If you go from one side to the next and look, your symmetry will work. So if you think these 2 points are the same coordinates, just different signs, well, you're right. Double check that. X is longer than the y. The x is longer than the y. So it's going to be 3, 2, 1 down, 3, 2, 1 up. Okay. That's it. That's the coordinates of all those interior points. Remember, the other ones should be easy pickings. 1, 0, -1, 0, 0, 1, and 0, -1. So that's all the coordinates around the unit circle. That's it. So in the time that's left, what we'll do is practice. In part 3, we'll pick up the tangent and where that comes from. Okay, so it's been real, it's been fun, I hope it's been informative. I hope everybody has a terrific Wednesday. See you next time.